For this lesson, we'll be reviewing the Laplace transform. Now, Laplace transform is the process of solving differential equations by an algebraic method. This is also known as the operational method. Now, why is this important to electrical engineers? Well, electrical engineers use it to convert original circuits, which is based on the time domain, and transform the circuit to the S domain or the Laplace transform domain. Now, once they do that, they can use algebraic methods, manipulate the equations, and then revert back to the time domain to solve whatever calculations we want to perform on that circuit. Now, this is very difficult to perform typical circuit analysis when you have multiple capacitors, inductors, and various AC sources on a circuit. So this is why we go to Laplace transform, manipulate the equations, and then revert back to the time domain using Laplace transform methods. So jumping right into the foundational Laplace transform is using the Laplace transform table. This is used for manipulating S-domain functions. And by using this table, you're able to convert the time domain functions to the S domain and vice versa. Now keep in mind, some of the equations provided here was from some of the PE references I have. Some of your sources may have more equations or less, just depending on which ones you use. Since the overall goal is to convert complex circuits to the S domain, it's necessary to understand how to convert each component to this domain. For the illustration we have here, we provided the resistor, the capacitor, and inductor, as well as AC and DC sources. Now just to keep in mind, the AC sources, off the bat, you have to refer to the Laplace transform table to convert your AC source to the Laplace transform or the S domain form. And now we're going to go over a little bit of this in the example though. Another very important conversion is charge capacitors and flux inductors. Now with charge capacitors, all you have to do is convert your capacitors to the S domain per the previous slide, but also add in a voltage source in series with this capacitor. And you also convert that to S domain as well. Or your other option is, go ahead and convert your voltage source to a current source, but put it in parallel with your capacitor. Now the same thing is also true with inductors. Inductors, instead, you just go ahead and add a current source in parallel with your inductor, or you could do source conversion and put a DC source or your voltage source in series with your inductor. And this is all using just basic simple algebra. Now just an overview of the steps before we get into exam problems is the Laplace transform steps. First thing you want to do is convert the circuit to the S domain. Simplify the S domain response. In other words, you're going to simplify the big equation down to as small as possible. Then you're going to determine the inverse transform using the table. So this is where you take that S domain response and you go and refer to that Laplace transform table to revert back to the time domain. And again, we're going to go over this in the exam problems next. All right, let's jump right in and get our feet wet with a somewhat easy one. For this one, we're going to determine the inverse transform of the following equation. Now for this one's not going to be very difficult, but just get our feet wet of how to use this table to our right. What I'm going to do is I want to actually go ahead and take this equation and break it up into its 4 pieces. But you can see a plus sign dividing each piece into 4 spots. So this one's going to be 1, 2, 3, and 4. And what I'm going to do is I'm going to find the inverse transform for each one of these, one at a time using the table. So it's going to kind of mimic what you see in the control systems function or your typical S domain function. Look at 25 over S here. Well, if you look to the right, what does it mimic on this particular table? Well, it mimics 1 over S, except there's a 25 there. So if you notice 1 over S equals 1, well, same concept. This is kind of your K when it comes to your S domains. So if you think of the control systems when you're doing Bode plots or any of those second order functions, this is your K, so which means K is always multiplied times your function. So whatever your equation is, it's always times K. So same thing here. So I have 1 over S, and it's going to be times 25. And that will give me 25 over S. And I'll tell you what, I'll try to put tails on these. So which means 25 over S would equal 25. So we're going to say f of t. Now keep in mind the cases. You'll typically see uppercase for Laplace transforms or the S domains, and then time domain you'll see it lowercase. So for this one, 1 over S is going to be 25 over S, which is 25. All right, then it's going to be plus. And then we have 5 over S squared. Well, again, looking down at this table, which one of these mimics 1 over S squared? Well, it's going to be that guy right there. And same thing, your 5 is going to be considered your K, so which means your 5 is going to be multiplied times your 1 over S squared. So which means you're going to have times T, so it's going to be 5 times t. See how I got that? All I did was replace this guy with t. All right, let's do number 3. And I might have to clean this up a little bit, but we'll see. So you have 2 over s plus 4. Well, same thing. We're going to refer to the table to the right. Which one does this mimic? Well, I see one right there. That's what it'd be the closest to. So I see 1, which is our k, which is going to be 2, over s plus alpha. So our alpha in this case is going to be the 4. That's going to be our alpha right there. So all I have to do is take this and convert it down. So I'm going to say 2 times, because again, you see a 2 right here, and then it's going to be e to the negative. And what is your alpha? Well, this one, we just determined it's going to be 4, and then times time. Look to the right, and then matching it with its time domain function. All right, last one. Tell you what, I'm going to clean that up right there to give myself room. So I have 13s over s squared plus 16. Look to the right. Which one of these has s in the numerator? Well, we got that one. No, and when we have that one. And I don't see any others with s in the numerator. So right away, it looks like I'm going to be using one of these two, which is going to be one of the cosine functions. And since my equation's not this elaborate, it's most likely going to be this guy right here. So I have 13s, which is good, that's my k. And then I have s squared, that doesn't change, plus 16. Well, that's where the tricky part comes in. Your goal is to go from 16, and you got to have a square. Well, the best way to get rid of that is go ahead and square root both sides. So which means that's going to give us a 4. So in other words, you're going to have 13, because again, that's going to be your k. That's going to be times your cosine. And then times 4, because we just determined that was 4, times time. And this part's not very difficult. It's just getting to know the table and how to manipulate a problem to fit your needs. So all you want to do is take what you see and actually find a way to match exactly what you see here. And the rest of it's just plug and chug. All right? So that will be our final answer to determine our inverse transform for this particular S-domain function. All right? Now that we got our feet wet a little bit with the table, let's go on to a circuit example. All right, for our second example, we got ourselves a really good one. This one, we want to determine the equation for our current in the time domain for this particular circuit right here. So we have a DC voltage source. It's going to a switch that's closing at time 0. It's going through an inductor, resistor, and a capacitor. So our goal is we want to take the circuit, which is in the time domain, convert it to the S domain, and then back down to the time domain to determine our final equation for current. So what I'm going to go ahead and do is I'll go ahead and leave the circuit here, but I want to go ahead and write on it and manipulate it. So this shuts at time equals 0. So right now I'm going to have a short right there, which means we're getting rid of that switch. Then when we refer to the PowerPoint slides, we said for inductors, all you have to do is add an S at the very end. Instead of henries, just put an S there. So instead of 10 millihenries, you put 10 milli S. And if you actually don't want the milli in there, it can be 0.01 S. All right. For resistance, just as easy. So instead of 2.7 ohms, you just go ahead and put 2.7. So this one's just going to be straight 2.7, which means your ohm symbol goes away. And the last one, now this one is usually what trips people up, is usually your capacitors. So for capacitors, you take your value and you do the reciprocal of it. In other words, for to go from time domain to S domain, you're going to say 1 over 20 millifarads. So which means you're going to have 1 over 20 millifarads. That's going to give you a 50. And then you do over S. So all you do is do the reciprocal and put S under it. So in other words, this one is going to be 50 divided by S. And again, I'll try to keep tails on it. That way you can see S from a 5. The last component we got to change is our voltage source. Well, instead of 12 volts, and since it's DC, you just go ahead and take 12 divided by S. Now the good news is, all we have to do is revert back to our circuit analysis fundamentals. This one's just using Ohm's law. So I want to determine current. Well, I have voltage and then I have resistance values. So when you see these values right here, think of these as resistance values, and that's actually voltage. So in other words, I'm going to look for I equals V over R. Well, I'm going to do the same thing in the S domain. So I'm going to say I of S equals V of S over R of S. That's the same thing I'm going to do. So I'm just going to revert back to my fundamentals. So here's what we're going to do. Let's go ahead and make our equation. We're going to say current is flowing in this direction right here. So I'm going to say it's I of S. Negative 12 over S, because that's your voltage source. I'm going to start with here, and I'm going to go up to my inductor, plus. My inductor is 0.01 S, and that's going to be times I of S. I'm just going to put I, just keep it easy on me. So that's our current. Then it's going to be plus, and then we have our resistance, which is 2.7, and again, times our current. That's going to be plus, and this is going to be our capacitor, which is going to be 50 over S, and that's going to be times I. And that's going to equal 0. So right now we have a very simple equation off the start. Well, let me clean this up. Let me go ahead and get our voltage source on the other side of the equation. So it's going to be 0.01 S times current plus 2.7 times current. It's a lot of rewriting here. It's our capacitor times current, and that's going to equal, and I'm going to add 12 over S to both sides, so it's going to be 12 over S. So far, so good. Voltage source, resistance values. Now I'm going to isolate current all by itself, so I'm going to say I times, and this is going to be 0.01 times S plus 2.7 plus 50 over S. And that's going to equal 12 over S. So nothing I did here was very difficult. It's just a little bit of simple algebra just to isolate a few things and keep it clean. So like we talked about earlier, we want to use Ohm's law and go ahead and say we got voltage here and we want to divide it by resistance. So in other words, I'm going to divide both sides by resistance, which is this equation right here. So I'm going to divide it by 0.01 S plus 2.7 plus 50 divided by S. I'm going to do the same thing over here. So it's 12 over S divided by, same thing, 0.01 S plus 2.7 plus 50 divided by S. All right. Let me go and clean this up and give myself a little bit of room. All right. So all I did was just clean this up and move our equation up here. So I have our current equals 12 over S divided by, and this will be our resistance. Well, just to keep this clean, let me go ahead and see if I can make it easier on the eyes. So I'm going to say 12 divided by, and this is going to be S, which is this guy right here, times 0.01 S plus 2.7 plus 50 divided by S. So that should be a little bit easier on the eyes. So we'll keep moving forward. What I'll do is I'll go ahead and move this S and multiply it inside this equation right here. So it's going to equal 12 divided by, it's going to be 0.01 S squared plus 2.7 S plus, and this is the great part, S times 50 over S. Well, the two S's will cancel out, so that's going to give you 50. But this next part I don't necessarily have to do, but I'm doing it just to try to keep these equations clean, and that way you can try to get a visual representation to match it with the equations we have in the table. So what I'm going to do is I'm going to isolate this S squared by getting rid of 0.01. I want to actually get S all by itself. So what I'll do is I'll take this and I'll divide each one of these by 0.01. Just like that. So it's going to come out to be your current equals 12 over, and this is going to be 0.01 times, so what I'm doing is I'm going ahead and isolating the 0.01. So it's going to be S squared plus, now 2.7 divided by 0.01 should give you 270 S plus, and then 50 divided by 0.01 should give you 5,000, or in this case, 5 kilo. And we're going to keep going. I'm going to say 12 divided by 0.01, and that's going to give me 1,200. And now we have a nice little clean equation so far. Now the last step I want to do is I want to see if I can take this equation and try to have it mimic something over here. Well, looking over here, the one that could probably do it is this one right here. I could probably find the quadratic roots of this equation, and I can use those roots to convert it back to the time domain. So what I'm going to do is I'm going to take my calculator, use the equation function, and then plug this into the equation function, and that should give me my roots. So by plug and chugging in there, it's going to give me an S1, negative 20, and then an S2 of negative 250. So in other words, our roots are going to be S plus 20, and then S plus 250. That's a simple way of actually finding out what your roots are going to be in your calculator without pulling out the quadratic formula. You can use our equation function and determine it that way. So in other words, your current is going to equal 1200 divided by, and this is going to be S plus 20, and then it's multiplied times S plus 250. And I'll try to put tails back on these. And I think right there, that's just enough to mimic this equation right here. So I'm going to move all this up and we'll see if we can knock this guy out. So looking at this guy right here, I'm looking at our table for number 7. We can say this guy is X and this guy is Y, which means all I have to do is plug and chug the rest into this equation right here. So I'm going to say I of t, because we're going back to the time domain now, it's going to be 1200, because we don't have a 1 here, we have a 1200 here. That's going to be over, and then we're going to have y minus x, so 250 minus 20. All right, and then e, and that's going to be times to the negative x, so we have 20 times t. And then plus, same sign inverse, we have 1200 on top on our numerator. And then we have x minus y, so we're going to have 20 minus y, which is 250. And that's going to be e to the negative y, which is 250 times t. Like I said, not very difficult, just breaking them down and actually finding a way to manipulate them to fit your needs. All right, and then plug and chug that in that calculator. We're going to say our current in the time domain is going to be 5.217. That's going to be e to the negative 20 t. Now right here we have a negative. 20 minus 250 is going to give me a negative. So this is not going to be a plus, it's going to be a minus. However, it's going to be the same answer, 5.217. That's going to be e to the negative 250. That right there is going to be our current in the time domain for this particular circuit right here. So this one wasn't difficult, just took a little time and a little ways to understand how to do the algebra and manipulate it to your needs. All right, let's do one last example. All right, for our last example here, it's not going to be necessarily harder. However, it's just to get our feet wet with as many practice problems as we can. Now for this one, we want to determine the current in the time domain for the inductor. So we're going to go through the same steps as the previous problem. We're going to take this circuit right here, convert it to the S domain, and then back to the time domain. Well, for this one, the switch is not closing, it's actually opening. So which means you're going to be isolating these components all by itself. Well, it looks like we have an initial current already on the inductor. So this current right here is already going 10 milliamps in this direction. Let's go ahead and begin. Let's go ahead and take this circuit and convert all the components to the S domain. So the first thing I'm going to do is get rid of the switch. Since it's opening, I'm going to go ahead and put it open right here. Then I'm going to go ahead and break down every component. Now for resistors, all we talked about earlier was, for resistors, all you have to do is remove is the ohm symbol. So for this one, it's going to be 1000. For our DC voltage sources, all you have to do is put an S under it in your denominator. So it's going to be 24 over S. Again, for resistors, all you have to do is put a 50 there, 100 here. And for inductors, all you have to do is instead of the H there, you just go and put an S. So this one's going to be 10S. However, this inductor is already fluxed. In other words, you already have current flowing through it. Since that's the case, all you have to do is add your current source in parallel with this inductor. So which means all I'm going to do is take this guy right here branch them out. Put a current source right there. That's going to be going in parallel. And that also means you're going to take your 10 milliamps and convert that to the S domain. So which means you're going to have 10 times 10 to the negative 3 divided by S. Now there is another way of handling this. I usually prefer dealing with voltage sources versus current sources, so there is another way to approach this. Well, looking at the slides, you're going to see that we can actually take this inductor and parallel with this current source and actually convert it to a voltage source, and that's what I prefer to do. So for this one, I'm going to put a voltage source right here instead of a current source. So I'll tell you what, let me go ahead and remove this current source, and right here I want to make a spot for my voltage source. So right here, I'm going to put a voltage source in series with my inductor. All I'm going to do is copy exactly what I saw from the PowerPoint. So I'm going to put a minus here and a plus here. And now we got to determine the value for this voltage source. Well, the good news is if you want to convert that, like we showed earlier, the current source is going to be 10 times 10 to the negative 3 divided by S. Well, if you want to do your voltage equals your current times your resistance. Well, for this one, this is going to be your resistance, which means 10 times 10 to the negative 3 times, and this is going to be your inductor, times 10 S. Well, the good news is when you do that, the S's cancel out, and you're multiplying 10 to the negative 3 times 10, which means you're going to have, instead of 0.01, you actually multiply it times 10, which is going to give you 0.1. So that's what our voltage is going to be right there. So it's not even going to be 0.1 over S, it's just going to be 0.1. So this one's going to be easy on me when actually making my equation. All right, so going back to our circuit, right off the bat, we can go ahead and take this guy off the list and this guy because there is no current going through either one of those. So right here, we're going to make an equation for this loop right here. So I'm going to do the same thing as I did as the last problem, but I'll start right here. I want to say, and we'll say that's I of S, of course. So we're going to say 50 times I. I would put I of S, but we all know what it is because I use uppercase. Plus, and for this one it's going to be 10S because that's our inductor, times I, and it's going to be minus 0.1 because we have our voltage source right there, and then it's going to be plus 100 times I, and that's going to equal 0. And same thing, I'm going to go ahead and isolate my voltage to the other side of the equation, so I'm going to say 50 times I plus 10S times I plus 100 I equals 0.1. So far so good. This isn't too bad at all. And of course I'm going to do the same thing, going to isolate my current all by itself. So I'm going to say my current is multiplied times 50 plus 10S plus 100. And that's going to equal 0.1. Now, going and simplifying this down a little bit more, you can see 50 plus 100 is going to be 150. So it's going to be current times 150 plus 10 to the S. So right now, this is cleaning up a little bit better every time we do it. Now let me do the same thing we did in the previous problem. I'm going to divide both sides by resistance. So our resistance is going to be 150 plus 10 to the S. This is our impedance or our resistance. So again, you just revert back to your fundamentals. And then it's going to be equal to also divided by 150 plus 10S. And that cancels out. So in other words, we're going to have current equals 0.1 divided by 150 plus 10S. All right. Let me make some room here and we'll see if we can keep going. Now continue on simplifying this problem down. Let me go and isolate S all by itself. My goal is to try to get S all by itself to try to mimic one of these. So I'm going to do the same thing. The best way to do it is I'm going to divide both sides by 10. So that means we're going to have 0.1 divided by, and this is going to be 10 times, and we'll go ahead and say S plus 15. And of course, 0.1 over 10 is going to give us 0.01, and that's going to be S plus 15. particles on there. So right now we just took that and made a very clean equation, and that actually mimics one of these guys right up here. And the one I'm looking at is right there. So which means if I want to take this and convert this, all I have to do is say, this is my K, so I'm going to say 0.01, and that's going to be times, that's E, and then our alpha for this one is going to be 15, so it's going to be negative 15, negative sign alpha, times time. And that will equal your current going through your inductor, and this is going to be in your time domain. Now the good news is if you revert back to our RL transient analysis video, this will also match up, because in that video we had I of t equals your initial current times, and this is E to the negative time over resistance and inductance. So if you actually plug and chug that in that equation right there, it's going to be I of t equals your initial current, which is 10 milliamps, times E to the negative t. Now you have resistance over inductance. Well, right now our total resistance was 150. So our resistance was 150, and our total inductance was 10 henries. So if you did 150 over L, or 150 over 10, that's going to give you 15. So look in this equation right here. You're going to have I of t equals 10 milliamps, which is going to be 0.01 times E to negative 15 times t. So this matches that guy right there. So right here, we proved how they came up with a discharge equation for inductors. We went ahead and took this circuit, broke it down to the S domain, back to the time domain, and it matched exactly what you used in the RL transient analysis video.